So we will begin with the Chapter 9 notes. And the first thing we're going to do is talk about language. Chapter 9 is not really different from Chapter 8. It's actually a continuation of Chapter 8. And your homework assignment for Chapter 9 is going to be actually a review of Chapter 8 and Chapter 9, which will help you prepare for the next test. The next test will also include Chapter 10, and we will do Chapter 10 next week. We've actually already done part of Chapter 10 back when we did Chapter 1, so we're going to just finish up with it. Yes, ma'am?
I have a question about the interpretation worksheet. Like, it used to be 3 pages. Did you change it?
I changed out the interpretation worksheet to a different one, and I posted the answers to the one that I gave, so you don't have to do the other one. But if you try to do the other one and you have a question about it, you can ask me the question, and I will reply to the question. But the one that I put in there is actually a better interpretation worksheet than the first one that I posted. Because I looked at the 2 that I had and I thought, well, this one's kind of long and it's kind of mixed up. This other one is kind of focused on just writing, actually doing the process and then writing the conclusion. Okay?
Thank you.
So what we're talking about in Chapter 9 that is different from what we talked about in Chapter 8 is that in Chapter 8 we were looking to test a claim about a population mean or proportion when we only had one population. What we're looking at doing now is we're going to compare 2 populations and try to decide if there's a difference between their means or their proportions. But the only thing that changed is the fact that we've got 2 samples now from 2 different populations, or possibly, and this is one little caveat, we have 2 sets of information from a single population that we're going to compare. And so for that reason, what we're looking at is just the same procedure with a different set of data. So our choices are still going to be the same. If we're talking about proportions, it's going to be a 2-sample proportion test. Okay? If we're talking about the difference between populations means, then we're going to be talking about a 2-sample, either z-test if we know sigma, which is the same as Chapter 8, or t-test if we don't know sigma for both populations, which is right in line with what we did in Chapter 8. And then at the end of this, when we're doing the review, I'll try to wrap this all up for you and tie it in a bow on Monday. I'll give you a flow chart that I will allow you to use on the test that helps you choose between a confidence interval, a 1-sample hypothesis test, or a 2-sample hypothesis test. And we'll talk about how you make those decisions. And we'll work on some practice problems for Chapter 8 and 9 on Monday, as well as add a few for Chapter 7, because that way you'll still remember your confidence intervals, because confidence intervals are going to be on your final exam, as will a couple of questions, maybe 3 from Chapter 9 and 2 or 3 from Chapter 10. And the reason I want to wrap up next week is so that we can go ahead and test and still have 1 day left in class to actually review in class for the final. Okay? So we'll get started here. First part is a vocabulary type of situation. 2 samples are independent. That's the word you're looking for here. Two samples are independent if the sample data from one population is completely unrelated to the selection of sample data from the other population. For example, if I wanted to compare the exam scores on the last exam for this class to the exam scores on the last test to my afternoon class, that's 2 different populations. You are not the same population that they are. I could consider you samples from the same population, but as far as being populations, you're totally different populations. Your test grades don't have any influence on theirs, their test grades don't have any influence on yours. There's no connection between the two. On the other hand, two samples are dependent. If each data value in one sample can be matched or paired with a corresponding data value in the other sample. For example, if I were talking about your test grades, we've now had 2 exam grades, and if I wanted to compare your first exam grade to your third exam grade, well, those exam grades are both coming from one set of people. So those are paired. I would be looking at Matthew's test 1 and test 3. I'd be looking at Chase's test 1 and test 3. I'd be looking at Kayla's test 1 and test 3. So those 2 pieces of information are actually coming from a single population. Even though the first group of test scores and the second group of test scores make up 2 populations, those populations are linked or paired. When you're testing the mean of differences of paired data values, this is the dependent. The null hypothesis always says that there is no difference. That's really the kind of the same thing that we did in Chapter 8, because what Chapter 8's null hypothesis could have been worded to say is there is no difference between this number and the actual mean of the population. When we say that the mean of the population is equal to this, we're saying there's no difference between the mean of the population and this number. They are the same. And in this class, remember, we can use any of those 3 symbols. They all 3 work. In turn, the alternate hypothesis or alternative, if you use the language alternative, but either one works, depends on the problem, and it can be either the mean of the differences is less than 0, the mean of the differences is greater than 0, or the mean of the differences is not equal to 0. This is actually the direct opposite of what the null says when there's no difference. The mean of the differences not being equal to 0 says, yes, there is a mean, a difference in the 2 means. I don't know whether which one's more and which one's less, but I know there's a difference. They're not the same. Okay? So this is with paired data values, and since this would always be what your alternative hypothesis would let you choose from, your HO basically is going to say the mean of the differences is equal to 0. Even though it may be that it's equal to or greater than or equal to or less than, the idea is that we're always going to have equal to. So we're going to go through a few examples here. And I think you're going to see with this first set of data, we're talking about whether or not simply are they independent or are they dependent. That's really all we're questioning here. Are they independent or are they dependent? So in the first problem, we've got a table that shows the heart rates in beats per minute of 5 people before and after they exercised. Now that is 2 different samples of data. We have their heart rate before, that's sample number 1, and we have the heart rate after they've exercised, that's sample number 2. But is there a link between those two samples? Are they paired in some way? Ella, what's the length?
Before and after?
Before and after. And where's that information actually? What's the link between before and after? Who's it coming from?
It's the same person.
It's the same person, okay? It's the same person. So since it's the same person, what we're actually looking at here is we are actually going to be looking at the mean of the differences. And that's why we use the notation UD. Because what we're actually going to do, what do you think happens to a person's heart rate before they exercise and after they exercise? You think it goes up. So you think basically that the mean of their before is less than the mean of their after, which means what you actually think is that difference is going to be negative. If this is smaller and this is bigger, that's going to be a negative difference. Okay? So while our null hypothesis here might say the average difference is 0, there is no difference in the two heart rates, then what our alternate hypothesis might say is the mean of the differences is less than 0, because that's how you calculate the mean of the differences. Okay? So this would be HO, and this would be H1. And we could actually calculate those differences by taking 65 minus 127, 72 minus 135, 85 minus 140, 78 minus 136, 93 minus 150, and we would see that all of these differences actually are negative. So then we would be able to calculate the mean of those differences and determine whether or not it's close enough to 0 to say, well, there really wasn't any difference, or is it more like this in our left tail hypothesis test. If we rejected HO, then we would say, yes, there is a difference. Their before rate minus their after rate is negative, meaning that exercise raises your heart rate. Okay, and we could come back and work this problem in a little while if we wanted to. So for this one, we decided that that one is dependent. That one's dependent. Sample 1 is the weights of 40 females. Sample 2 is the weights of 40 males. Is there any connection between those two sets of weights? Any pairing? No. These people are not, they're not related in any way. Even if we said, we take all the male and female siblings, they might be, children of the same parents, but that's not a connection about weight. They're not necessarily going to have a connection about their weight just because they have the same parents. So the connection has to have to do with their weights. Here, the connection had to do with the heart rate, and those heart rates were coming from the same person. If we had the heart rates of 40 females and the heart rates of 40 males, still no connection because it's different people. We're collecting the data from different people. So that means this one is actually independent. There is no logical connection that we can think of that would make their weights related to each other in any way. So here's our second example, and all the rest of these are going to be actually word problems that show you how the word problems in Chapter 8 work. And know, so that you'll know what to look for when you're trying to work these word problems. So you want to buy a vacuum cleaner. Salesperson tells you that the repair cost for the Model A vacuum cleaner and the Model B vacuum cleaner are equal. They're the same. You research the repair costs of 34 Model A vacuum cleaners and 46 Model B vacuum cleaners, and you find that the mean repair cost from the Model A was $50. You also found a previous study, and this is information that, we kind of perk up and listen to because it says, oh, previous study, we've got some information from the past. That says the standard deviation of all repair costs for Model A was $10. Remember that. You find that the mean repair cost for your 46 Model B samples was $60, and you also found information that says the standard deviation of all of Model B vacuum cleaners was $18. So at the 0.01 level of significance, we know what that means. Can you reject the salesperson's claim? So the first question we need to ask is this independent or is it dependent samples?
Independent.
Independent because are they costs from the same model of vacuum cleaner?
Yeah.
No. There's no connection between those two. And in fact, one of the ways you'll know for sure that you have what's called an independent sample is if the size of your sample isn't the same. Okay, that's going to be a big giveaway. If you have a sample of 34 of Model A and 46 of Model B, well, you can't pair those up because you got more of one than you do the other. So if you have different sample sizes, it's guaranteed that you have an independent sample. So these are independent samples. And because they're independent samples, we are going to do a 2-sample test. Question is, which 2-sample test will we do? Z or T? How do you always decide between Z and T?
If you have standard deviation in the population.
Okay. Do we have the standard deviation of the population? Yeah. This is sigma for Model A. And this is sigma for Model B. So yes, we have the population standard deviation. Therefore, we will do a 2-sample Z test. And that's because sigma 1 and sigma 2 are both given to us. So we're going to fill in the chart that we have here. And X bar 1, in fact, everything sub 1 is going to represent Model A. And then X bar 2 is going to represent Model B. And so is sigma 2 and N2. And it's not because it has to be that way. We could do it the other way around. But we just need to identify which one's going to be which. So that when we come to our conclusion, we'll know how to say our conclusion. So looking first at Model A, says the mean repair cost for Model A was $50. and the size of n was 34, and sigma was 10. So we fill in that information. And then for model B, it says that the mean was 60, standard deviation was 18, and you were looking at 46 of the vacuum cleaners. So 46 vacuum cleaners with a population standard deviation of 18 and a mean of 60. Now we can see obviously, yes, there is some difference in the repair costs. But also take into account that the spread of the values of the repair costs was very different for both. And that could mean that even though this looks like a smaller difference, maybe this larger variability says that's really not that far. So we have to look at both mean and standard deviation. And the sample sizes really doesn't help us out either way. You just need to make sure that you've got a sufficient sample for both. So what we need to do now is we need to set up our hypotheses. And that means we're going to write the claim, which is always step one. Can you reject the salesperson's claim? Well, what did the salesperson actually claim? That the repair costs for Model A and Model B are equal. Okay? mu sub A is equal to mu sub B. There is no difference. Now, if we're going to be able to reject that claim, then what would our claim be?
The mu is not equal.
Now, they're not equal. Now be aware that this could also be written this way. Because both of those say there is no difference. This one could also be written that way. And that way basically said, yes, there is a difference. There is a difference between the two.
So I'm confused. Why are you writing that one? Like, since it's not the claim.
You always have to have your claim in the alternate because either the claim is true or the alternate is true. Okay? So basically what the alternate says, well, what this claim says, what the opposite of the claim says is there is a difference. Okay, there is a difference between the two. So given that we have these two, regardless of who's the claim, because we never care who's the claim when we're setting this up, which one of these is HO and which one is H1? What does HO have to say? Equals. There is no difference. So here's our HO. Running out of colors. is because of this. That means this is H1. And it could be written, as I said, either way. There's no reason to write either one in particular. You can use it interchangeably, whichever one makes the most sense to you. So we're talking about differences, we're talking about subtractions. Okay? So we're going to use the calculator to find the test statistic and the p-value and make a decision. So we're going to get the calculator. And I'm going to go, as we usually do, to the test menu. And this tells us that we're going to choose the two-sample z-test. Okay? The two-sample z-test is the third option on the menu. Once I've chosen that third option, I have to tell it, is my data the input, or do I have only statistics? Well, I don't have the actual cost of either vacuum cleaner, so I have statistics. And just like it did before, it asks questions about the values of the problem. It says, and since we're using model A as being group 1, it says what's the population standard deviation for model A? And it's 10. Then it asks us, okay, what's the population standard deviation? Since model B is 2, what's the standard deviation for model 2? And that's 18. And then it says, what's the mean of your sample from model A? That was 50. And then how many were in that sample? Well, there were 34. And then what's the mean for the sample from model B? That's group 2. Well, the mean for group 2 was 60. And the sample size for that group was 46. And then the next line, as it usually does, says, okay, what does H1 say? Well, here's what H1 says. H1 says not equal to. And then you have the choice that you usually have, calculate or draw. Okay? So I'm going to summarize what we have put into the calculator to make sure that you know what it is and can write it down. So what you're going to do to show your work is you're going to make note of the fact it was a two-sample z-test, that your input was from statistics, that your standard deviation for model A, remembering that model A is group 1, was 10, and the corresponding standard deviation or population standard deviation for model B was 18, and then the mean and the sample size for model A, which is group 1, was 50 and 34. And then for model B, same information, 60 and 46. And then this is always, what does H1 say? I'll cover it all up. is always going to be what does H1 say. And H1 is that mu1, notice it puts you mu1 first. And what we're saying is H1 says mu1 is not equal to mu2. That's actually the more common way to write it, not that the actual difference is 0. It's usually just the inequality between the two. And then our next choice, as usual, is calculate or draw. Now I am actually going to calculate at the end of this to show you what the difference of the two is. But for now, we're just going to draw. Now I want you to remember this is a two-tailed test. Because does not equal is always a two-tailed test. So let's look at this picture and see what it tells us. The center of the curve is where the two of them are equal. This is where the differences are negative. One minus 2 would be negative because 2 is bigger. This is where the differences would be positive. 1 minus 2 would be a positive number because 1 is bigger. Okay, so basically, these are the three things that could happen. What they tell us here is that our test statistic, remember that comes from your sample, your test statistic is negative 3.1647. So that's where your test statistic actually falls. But because of the fact that it is a two-tailed test, we took the p-value that came from this and multiplied it by 2, or your calculator did, and said, you know, just because it happened to turn out to be that way on this sample, also, since you did a two-tailed test, it's just as likely it could have happened that that difference had been a positive difference and it would have fallen on the other end. And that's why you have a total p-value. But the thing is, your total p-value right here is less than a dot, and here's less than a dot, because your total p-value, which again comes from your sample, your total p-value is 0.0016. Okay? So since we have a p-value that's 0.0016, and we started off with an alpha value that was 1%, is p less than alpha? Yes. And what do you do if p is less than alpha?
Reject.
You reject HO. And if you reject HO, what does that mean about the claim?
The claim there's no evidence to support the claim.
There's no evidence to support the claim. So HO was the claim. Therefore, the evidence does not support HO. there's your conclusion. You reject HO because P is less than alpha. That means HO is not true, but HO is the claim. So the claim is not true. Evidence from the two samples does not support the claim that the repair costs for A and B are equal. The difference was not 0. There was a considerable difference between the two. So as I said, I'm going to go back over here and I'm going to run the test again. Only this time I'm going to calculate, and I'll show you what you see when you calculate. If you calculate, notice that it repeats H1. Just to remind you, that was what you said. Then it gives you the p-value. Which matches up with the p-value here that we got to begin with. Matches up with our 0.0016, just been rounded. It repeats the mean of sample 1 and the mean of sample 2 and the sample 1 size and the sample 2 size. But the thing is, it didn't give you the actual difference. What was the actual difference between population 1's mean and population 2's mean? $10. And since population 1 was less than population 2, A was less than B, that difference is negative, which is why our test statistic fell down here. Now, we could have actually known what the difference was when we started out and knew that it was negative, but we didn't really need to know that at the moment. All we needed to do was run the hypothesis test and at the end see why it comes out the way that it does. And it comes out the way that it does because we had a two-tailed test. Our sample fell into the left tail because our difference was negative. But because our claim was they were equal and our alternate was they were not equal, that means we have to also assume that difference could have been the other way. It could have favored the other way. Okay? Any questions? Is this terribly different from what we did last class? Not really. It's pretty much the same steps. It just has one additional step, and that one additional step is are your samples independent or dependent? Are they paired or are they not? Okay? So let's look at another example. Advertising executive claims that there is a difference. There is a difference. In the mean household income for credit card holders of Visa Gold and MasterCard Gold. The results of a random survey of 100 customers from each group is shown below. We want to test the executive's claim at a 5% significance level. So we have some information here that'll help us test the claim, but first we have to set up the hypothesis test. And before we can set up the hypothesis test, we need to know if these two samples are independent or are they dependent. Is there a natural link between those two sets of data? No. The only way there might have been a link is if the problem had said that the cards were for the same customer. If you had 100 customers and they had both cards, and there's no difference in the balance they carried on their two cards. Okay, that would have made it dependent. But this is two different sets of people. Some of these people have Visa Gold, some of these people have MasterCard Gold. There's no link between these people. So this is independent, two sets of people. Therefore, two sets of card balances. Our next decision is it we already know it's a two-sample test because we got group 1 and group 2. So we know it's not a t-test. We know it's not a z-test. I'm sorry. There should have been a z-test in there. So we know it's not a z or a t-test alone. It has to be a two-sample test because we have two samples. Do we have the information that will let us do a z-test?
No.
I had a question, about the previous question.
Okay.
If it was dependent, what would we do differently than if
You're going to see that in the next example. Okay? Right now in this one, I only wanted you to know how you might think it was dependent if they had given you a little more information that would have lengthened. But right now, we know it's independent.
Will these always usually be two simple tests? Or
Not always. Not always. When we have a dependent sample, then we're not necessarily going to have two samples. We're going to have one sample of differences. And we are going to do a problem like that so you'll be able to see how it works differently. But you already know the process for doing that one because it actually is the same as it was in Chapter 8. Okay? So, we don't know sigma, right? Sigma's not being given for either one. In fact, what we know is sample standard deviations. We don't know population standard deviations. So for that reason, we're going to do a two-sample t-test. And that's because in this case, sigma is not given. So we can't choose z, we have to choose t. Our values are already summarized. We need to set up our hypotheses and make sure we've identified the claim. Which one is the claim? Okay, at the very beginning of the problem, they claim there's a difference in the means. So there's our claim. If that claim is not true, then it says there is no difference. Which one would be H1? Which one would be H2? Top one's always HO. I think I said that bad. No, top one, I think I said H1 and 2. HO, the null, always says there is no difference. It has an equal sign. That means this is H1. Okay? So again, we're going to do exactly what we did before. We're going to use the calculator to find the test statistic and the p-value and make a decision. So this time we're going to go to the test menu. And this time we're going to choose a 2-sample t-test. And we have statistics. And X sub 1 is given to us as $60,900. X sub S for 1, this is for the first sample, is $12,000. And our sample size in 1 is 100. And then we're going to repeat the same thing for our second group. X bar 2 is 64,300. Standard deviation for that group is 15,000, so a little bit bigger. And our sample size is the same. And then the last thing is what does H1 say? And H1 says not equal to. And then it asks us questions that we didn't get asked before. Okay? I'm going to go to the next slide for a second. It's asking us, do we want to pool the variances or do we not want to pool the variances? You can pool the standard deviations or variances, because those are actually not one and the same, but if one's equal, the other ones are going to be equal. You can pool the standard deviations only under certain circumstances. The question is, if the two sample standard deviations, or if you're given the population variance, the population variances are sufficiently close. Now, I don't know about you, but I'm not feeling much in the way of judgment about, I don't know if they're close enough or not. How big is big enough not to be close enough? So, I don't feel like I want to judge that. Or if there is reason to believe that the population standard deviation or variances are equal. There again, unless somebody tells me they are, I don't want to make that judgment. I don't know, is $1 close enough, or does it have to be $100 to be close enough? I don't know what's close enough. I don't know if they are equal. That can only occur actually if you make a slight change or alteration to a known process or method of production in some kind of manufacturing. Like if you just perform some kind of maintenance on a line that fills cereal boxes and you're wanting to make sure that it's hitting the new mean, you could make the assumption that the adjustments you made didn't change the standard deviation from what it was before. It only changes the mean. But since we're not usually the ones making those changes, then we're not going to want to judge any of that. So here's my conclusion. You never pool unless you're told to do it. Okay? The only one exception to that would be if they actually tell, if I actually have these values and I can see with my own two eyes that they are exactly the same. If they're off by 10 cents, I don't care. They're not the same. And I'm always going to say, I'm not going to pool. So, to borrow a slogan from a different campaign, just say no. Unless you're told to say yes, just say no. So when I bring my calculator back up, I'm just going to say, no, they're not, period. And I am never going to change that unless they tell me the standard deviations or the variances are equal. If they tell me that, then I'll say yes. But if they don't tell me that, nope, rather safe than sorry. And there again, not last choice is either calculate or draw. So we're going to draw because we can calculate our own difference at the end if we want to. In fact, it's easy to see that yes, this mean is bigger than this one. It's bigger than that one by $3,400. I had to think about it for a while. You did better than I did. So here's what we get when we actually get the draw menu. It says that our test statistic is negative 1.77. That puts us there. So this is our sample. But remember, since this was a two-tailed test, they double the p-value in two-tailed tests. Just in case. Because it could have been that you had the same difference, but it could have been the other way around. They also do this because if you flip group 1 and group 2, the only thing that's going to happen is you're going to wind up here instead of down here. So that's why they double it. So your p-value is 0.0783. And from the statement of the problem, our alpha value was 0.05. Is P less than alpha? No. P is greater than alpha, not less than alpha. So our conclusion is we do not reject HO. Okay? We do not reject HO. But now we have to determine what that means. We have to write a conclusion. We do not reject HO. We keep HO. We have no evidence to support H1. So the claim was H1. There is no evidence to support the claim that there is a difference in the mean household income for cardholders of the two cards. We basically just answered the question. Okay? Any questions?
I have a question about the pooling.
Mm-hmm.
The question only comes up when you do a two-sample t-test. I like the information about the population standard deviation useful. Because if you're doing a t-test, then you don't know what population is doing.
That's true. That's the other reason I said just say no. Because, I mean, even if your sample standard deviations are equal, that might not, I mean, since they're estimators of the population standard deviation and they're close, chances are the population standard deviation probably is close enough to be equal if the sample standard deviations come out to be exactly equal. But I don't think there's going to be a lot of cases where you're going to have the sample standard deviations come out to be exactly equal. And that's why the safest thing to do is just say no. Okay? In fact, the only thing that's going to happen is that you are a little more likely to make a type 1 mistake if you just say no. A little bit more likely. Because if you can say, yes, pool the variances, sometimes if the p-values, if the standard deviations and the variances really are close enough, sometimes changing to a pool test from a non-pool test is enough to let you reject HO when otherwise you wouldn't. Okay? But that's a good question. That's a very good question. We're going to do another one. We've actually got 6 examples to do here. Random sample of finalists in the British Open gave the following data for the first and last rounds of the golf tournament. Does the data indicate that the population mean score on the last round is higher than on the first round?
We don't have any more examples in our notes.
You don't?
Yeah, it was just 2 pages in there.
Okay. Let me go ahead and work this one and I'll send these to you. So I'm going to let y'all walk with me through this one. I want us to do this one because this is one that you're asking me about. So the question is the mean score on the last round higher than the first round? Anybody here play golf? I don't. I hate the game. I do know that generally your score on the first round is usually your better score. And that's from talking to people I know that do play golf. They tell me that that's the case. Now, to me, it would be logical that your score on the last round would be the better score because you've already played the course once and you know what the course is like. But, you know, I don't know which one's true. So we're going to use a 5% level of significance and see if the data indicates that the population mean score on the last round is higher than it is on the first round. We're going to use the 5% level of significance, and somehow that just got repeated. So we can kind of ignore that last one. Now this is the big decision you've got to make, and this is going to change how we work the problem, so you've got to be sure you're making it correctly. Is this an independent or a dependent sample? How do you know it's dependent, Matthew?
Because it's the same people, like the first round and the second round.
Right, it's the same people playing. This is player number 1, player number 2, player number 3, player number 4, player number 5, player number 6, player number 7, player number 8, player number 9. So, this is dependent. What that actually means is we do not have 2 independent samples. We have 1 sample of differences. And what the claim is going to be is going to let us decide which way we want to write, which is first, which is last. So what they're claiming is that the last is higher than that on the first. And if the last is higher than the first, then we take their after minus before. The last round occurs last. And their score on the last round is the higher one. What kind of differences are we going to find? If this is the higher score and this is the lower one, are the differences positive or negative?
Positive.
Those differences are going to be positive. Now, if you wanted to turn it around and do first minus last, you could do that, but then you're looking for the differences to actually be negative. So that's why it's very important, and the conventional way that you're always going to do differences is always going to be after minus before. Okay, it's always going to be the last set minus the first set. That'll keep you from getting mixed up. This is a 1 sample test, so it's not 2 sample, not 2 sample. We are not given a population standard deviation. This is going to be a plain old t-test. It's just going to be a t-test. We're still going to work the whole entire problem on the calculator. You're going to need to pay careful attention to how I do this. And then I'll send you these notes and we'll finish these up next time practicing. The first thing I want to do is I want to actually enter the data because I don't have the statistics. I actually have the data from the 2. So for the first player, player number 1 on their first round made 66. Player number 2 shot 70. 3 shot 64. Player 4 was 71. Player 5 was 65. Player 6 was 71, 7 was 71, 8 was 71, 9 was 71. So you have 9 players. Player 1 on the second round shot 73. Their score went up. Player 2 shot 68. Theirs went down. Player 3 shot 73. Theirs went up. Player 4 didn't change. Player 5 also went up. Player 6 went up a little bit. Player 7 went down. Player 8 went down. Player 9 went up. But it wasn't just that they went up or down. What we want is their actual differences. So this is how you find the actual differences. And you could sit here, rather than do what I'm about to do, you could have sat there and said 73 minus 66 and entered the difference. And 68 minus 70 and entered the difference. That would have worked. But another way to do it is to actually go in here, instead of calculating those individual differences, tell it to subtract list 2 minus list 1, and it'll do that for you. Okay? It will actually do all the differences for you. Now, the other way you could have done it would have been to calculate your differences one at a time. 73 minus 68. Or, I'm sorry, 66. And 68 minus 70, and so forth. So you could do it one at a time if you wanted to. Yes, Lisa?
I got an error when I tried to do that.
Are you sitting up on top of L3 or are you sitting in L3?
Oh, I was sitting in it.
Okay, you have to be sitting on top of it. You have to actually have your cursor sitting on top of the list name. Anytime you put your cursor on top of a list name, it lets you do arithmetic with your lists.
Thank you.
And you could do it, like I said, you can do it either way. You don't have to do it that way. You can do each one individually. And you'll get the same result. So it's up to you. But that way is a little bit of a shortcut. So I put my differences in list 3. We need to remember that. So we're going to go down and choose the t-test because we're only interested in that single set of differences. Now before we go any further, set up your hypotheses and identify the one that represents the claim. Okay, we need to go back and look at the claim. The claim appears to be the population mean on the last round is higher than the first round, which, as we said, meant that if this is bigger than this, then those differences are going to be positive, which means the mean of your differences, and that's where that mu d came in on the first page, is greater than 0. Greater than 0 means positive. So this is the mean of all players' differences based on a sample of players. And if that's not true, remember this is the claim, then there is no difference. After minus before is going to be the same. And that's what tells us that our claim is H1. Because we have the inequality. Now we'll go set everything up on the calculator. We are actually working this time from data, not from statistics. The claimed mean is 0. There is no difference. My differences are in list 1. I'm sorry, list 3. So I changed list 1 to list 3 on mine. If you actually subtracted the individual differences, yours might be in list 1. It's okay either way, just be sure and tell it where they are. And then this, as it usually does, says what's the sign in H1, and the sign in H1 is a greater than sign. So we will draw, and this is a right tail test because of the greater than. I see a lot of shaded in area in the right tail. There's my p-value. And this is my test statistic. My t-value is 1.333. And my p-value is 0.1096. And my value of alpha is 5%. Is p less than alpha? P is greater than alpha. We do not reject HO. HO says there's no difference. Evidence from the sample indicates that there is no difference in the scores. So what we see here is that the average difference was about 2 points between their scores. Okay, it is a positive difference. The sample scores were, by and large, more than the population, or more than the last scores were higher than the first scores. Okay, there was a positive difference. However, that's not a big enough difference to say that that's always going to happen. Okay? So without me going through the rest of the examples, do y'all have any questions? Okay, there is a worksheet that has Chapter 8 and Chapter 9 problems on it for y'all to work on. Go ahead and start working on it. I posted the answers. So go ahead and start working on it. And we will finish up some examples and do that practice worksheet in class on Monday. And then we'll talk about Chapter 10. Chapter 10 probably will be Wednesday. I probably will do Chapter 10 on Monday. Yes?
So for when they're dependent, we're always just going to subtract the
Exactly.
sections.
Exactly. When they're dependent, you're always going to simply subtract. And remember, in order to keep from being confused, it's always after minus before. Okay, and if you think about it, that makes sense, because when you go on a diet, you want to lose the weight, so you want your after weight to be lower than your before weight if you're trying to lose weight, and that means you want your differences to be negative, you want to weigh less. And the same thing with test scores. If I were to give you a pre-test and a post-test, I would want your post-test scores to be higher than your pre-test scores, because hopefully in between I've taught you, and then that way you'll do better on your second test than you did on your first attempt when you're supposed to not know anything about it. Okay? So those are kind of situations where you might have dependent samples. Okay? I will go ahead and post the other examples so we can do those at the beginning of class next time. I didn't realize that it did not post all 6 problems. So y'all get out early today. And it's pretty outside. Let's sit in the sunshine.